There is a star out there so small that if we placed it beside the Sun, it would not feel like a rival. It would feel like a reduction, a stripped-down version of what a star is supposed to be. And yet around that faint red object, astronomers have now found a giant planet, a world large enough to belong to a richer system, a heavier nursery, a place with more raw material to spend. The discovery is strange on its face, but the deeper shock is quieter than that. It is the realization that one of the most ordinary kinds of stars in the galaxy may still be hiding planetary lives we taught ourselves not to expect. If you like videos that take one strange fact and keep pulling until the whole picture shifts, you're in the right place. Settle in, because this one gets larger the longer we stay with it. We tend to carry a childlike drawing of the cosmos in our heads long after we stop noticing it. Big stars feel important. Small stars feel minor. Large planets feel expensive, as if they ought to form in places with a lot to work with. That instinct is not foolish. It is built from patterns that do show up in nature, but it also smuggles in a confidence that the universe has never really granted us. The star in question is called TOI-6894. It is a red dwarf, the kind of star that does not dominate its surroundings with the theatrical force we associate with something like our Sun. Red dwarfs are dimmer, cooler, lighter. They are the quieter population of the galaxy. If the Sun is a bright public building, a red dwarf is a lit window at the far end of a street. Still real, still burning, just easier to underestimate. And that matters, because under the most widely used picture of how planets form, the size of the star is not just cosmetic. It is entangled with the amount of stuff available at the beginning. Stars do not emerge alone. They form inside clouds of gas and dust. And around young stars there are disks, broad, rotating reservoirs of material from which planets can eventually assemble. Bigger stars tend, in broad terms, to come with more substantial disks. Smaller stars tend to come with less. That simple fact does not decide everything, but it sets the budget. So when astronomers found a giant planet around TOI-6894, the discovery landed with the force of a receipt that does not make sense. You glance at the total, then at the itemized list, then back at the total again. Somewhere between the available materials and the final product, the story stops feeling comfortable. The planet is called TOI-6894b. It swings around its star in just a few days, crossing in front of that faint red surface from our point of view, and causing a measurable dip in the starlight. That is one of the most beautiful things about modern astronomy. A whole theoretical disturbance can begin as a slight dimming, a tiny change in brightness, recorded by a space telescope that never touches the planet, never sees oceans, or storms, or cloud bands directly, never hears anything. It watches light. The light changes. A world appears. And this is not some borderline object that barely qualifies as a planet worth mentioning. It is a giant planet, roughly Saturn-sized in radius, though lower in mass than Jupiter and puffier than the gas giant most people first picture. It is large enough that the mismatch is impossible to ignore. The star looks underfunded. The planet looks overbuilt. That is why the phrase "should not exist" keeps attaching itself to discoveries like this, even when astronomers are careful, and they usually are. It is not that nature has violated logic. It is that our working expectations had hardened into something that felt much firmer than it really was. The trouble is packed into the word "should." It sounds objective. It feels almost physical. But often it means something narrower. It means, given our current models, our current statistics, our current habits of explanation, this is not where we expected to find this. That difference matters, because the universe has not started misbehaving. We are the ones encountering the edge of our comfort. To see why the discomfort is real, it helps to slow down and stay with the mechanics for a moment. In the most familiar version of giant planet formation, you begin with a growing solid core. Dust becomes pebbles. Pebbles become larger bodies. Larger bodies collide and accumulate, and eventually, a core becomes massive enough to begin pulling in large amounts of gas from the surrounding disk. Timing matters. The gas in these young systems does not stay around forever. If a would-be giant planet cannot build itself quickly enough, the opportunity narrows and then vanishes. The disk thins, the window closes. Around a hefty young star with a richer disk, that process is already difficult enough. Around a much smaller star, the challenge becomes sharper. There is less material to work with, the construction site is poorer from the beginning. You can think of it as a village workshop somehow turning out an ocean liner, or a pantry that looks barely sufficient for dinner producing a banquet. The issue is not that we cannot imagine unusual success. The issue is scale. There seems to be too much planet for the account balance. What makes the discovery more than a curiosity is that red dwarfs are not exotic fringe objects. They are not the aristocrats of the stellar world. They are the majority. Most stars in the Milky Way are small, cool, unshowy red dwarfs. So when one of them turns out to host a giant planet that strains the rules, the consequence is not confined to one weird corner of the sky. It leaks outward into a much larger question. If our expectations are brittle here, where else are they brittle? And how much of the galaxy have we quietly been interpreting through assumptions that work well enough until they don't? That is the larger unease hidden inside this discovery. It is not simply that one faint star has an oversized companion. It is that the common settings of the universe may still be less understood than the dramatic ones. We spend a lot of time thinking about rare explosions, monstrous black holes, stellar collisions, and all the loud events that announce themselves. Meanwhile, the galaxy's most typical stars go on by the trillions, dim and persistent. And one of them now seems to be telling us that typical never meant simple. There is something almost humiliating about how these revelations arrive. Not humiliating in a cruel way, humiliating in the old scientific sense, the useful sense, the sense of being reduced to accuracy. We build theories carefully, we test them, we refine them, we learn genuine patterns. Then a faint star many light years away dims by a small amount, and suddenly the comfortable shape of the map begins to buckle. That buckle is the story. Because a planet like TOI-6894b does not merely ask to be added to a catalog. It asks a more interesting question than that. It asks whether our picture of small star planetary systems has been too neat, whether we have mistaken a strong trend for a hard boundary, whether we have been treating the commonest stars in the galaxy like modest neighborhoods with modest architecture, only to discover the occasional impossible house rising behind the trees. And once that image enters your mind, it becomes difficult to leave it there as a single oddity. Because astronomy has seen this kind of tension before. One strange world can be filed away as an exception. Two begins to feel awkward. A few more, and the pressure changes direction. At that point, the planets are no longer the problem. The theory is. That does not mean the theory collapses in a dramatic heap. Science is usually less theatrical than people want it to be. Models bend before they break, and very often they survive by becoming more honest about where they were weak. But bending matters. A rule that once felt sturdy enough to guide expectation becomes something more conditional, more nuanced, less satisfying to summarize in a sentence. And the sentence is what many of us were carrying around without noticing. A lot of the discomfort here comes from how natural the older intuition feels. If a star has only a fraction of the sun's mass, then the disk around it should also tend to be modest. If the disk is modest, then building a large solid core before the gas fades away should be difficult. If that core forms too slowly, no giant planet. The logic has a clean shape to it. It is not superstition. It is physics filtered through observation and simulation. Which is exactly why a system like this is so useful. It does not challenge a lazy guess. It challenges an explanation people had reasons to trust. What we are watching, really, is a tension between averages and outcomes. Nature often behaves in trends rather than laws of habit. Averages tell us what tends to happen. They do not guarantee what any one system will do. But human beings, and sometimes the language around science itself, are very good at letting a tendency harden into an expectation, and an expectation harden into a mental border. Past that border, things start feeling forbidden. Then, a planet appears there. TOI-6894b was first noticed because it crossed in front of its star and briefly blocked a fraction of the light. That is the basic elegance of the transit method. A telescope like TESS stares at huge numbers of stars and watches for tiny periodic dips, regular little notches in the brightness that suggest something is passing across the stellar face. When those notches repeat with the right timing and shape, astronomers begin to suspect an orbiting body. Follow-up work then has to rule out imposters, because the sky is generous with ways to be fooled. A background binary star can masquerade as a planet. Instrumental noise can suggest structure where there is none. A candidate is not yet a world. So the discovery path is quieter and more patient than the headlines imply. First a flicker, then repetition, then scrutiny, then the slow tightening of confidence. There is something worth pausing over in that process, because it is easy to say, astronomers found a planet, as if someone simply looked through a telescope and saw a globe hanging there beside a star. That is not how this works. We infer. We measure small effects. We cross-check them. We derive the size of the planet from how much light is blocked, and the nature of the orbit from how often the dimming returns. Other methods can help constrain mass. Piece by piece, a world takes shape not as an image, but as a converging argument. And in this case, the argument led to something awkwardly large for its setting. The host star is so small that the transit itself becomes part of the psychological shock. Around a larger star, a planet of this size would still be interesting, but the geometry would not feel as insolent. Here, the world claims a surprisingly large share of the stellar disk as it passes. It is like watching a parade float circle a porch light. The star is still a star, still a nuclear furnace, still incomparably more massive than any planet around it. But visually, relationally, intuitively, the pairing feels wrong enough to pull you out of old habits. That mismatch is one reason these systems attract so much attention. They make abstraction visible. If the whole issue lived only in equations and formation papers, it would remain important but not memorable. What gives it weight is that we can actually feel the imbalance. A very small host, a very large planet, a close orbit, a dim star briefly giving up a noticeable amount of its light because something substantial keeps crossing in front of it. Even before we discuss theory, the scene has a physical unease to it. Then the theory arrives and explains why that unease is not just aesthetic. Young planetary systems are races against loss. Material does not sit around forever waiting for planets to decide what they want to be. Gas disperses. Radiation alters the environment. Collisions build some bodies and destroy others. Migration can shift planets inward or outward. Timing and circumstance matter so much that two systems born from broadly similar ingredients can still end up looking very different. That part has always been true. What discoveries like this do is force us to ask whether one of the broadest assumptions in the background has been too confidently phrased. Maybe some low-mass stars occasionally begin with disks richer than expected. Maybe some local concentration process helps solids build up faster than the simple picture suggests. Maybe migration carries planets inward after they formed farther out, though that only solves part of the mystery, because the planet still had to be made somewhere. Maybe there are formation channels that become important in rare corners of parameter space, not often enough to dominate the population, but often enough to matter. None of those possibilities is magic. The interesting part is that we do not yet know which combination of them deserves the most credit here. That distinction between detection and explanation is one of the healthiest things to preserve in a story like this. Astronomers are not unsure whether the planet exists in the way casual language sometimes suggests. The object is the grounded part. The uncertainty lives downstream, in the account of how such a system came to be. There is a temptation in popular science to make uncertainty sound like weakness, as if not knowing every step means knowing nothing. But uncertainty is often the sign that the field has reached a live edge. The planet is real. The discomfort is real. The mechanism remains under negotiation. And that makes the discovery better, not worse. Because once a planet becomes too easy to explain, it slips into the furniture of the universe. It turns from revelation into inventory. A system like this stays alive in the mind because it resists being put away. It keeps pressing on the phrase, around that star, asking what exactly we thought that star was allowed to do. The answer, until recently, was something more limited than many people realized. Red dwarfs were already known as important targets in exoplanet research for practical reasons. Their small size and low brightness can make certain planets easier to detect. If an Earth-sized planet crosses a small star, the relative dip in light is stronger than it would be around a sun-sized star. The habitable zone also sits closer in, which means shorter orbital periods and more frequent transits. That is part of why red dwarfs became central to discussions of potentially rocky, potentially temperate worlds. But gas giants were supposed to be a different matter. Small rocky planets around red dwarfs fit the budget. Giant planets were the expensive surprise. That is why a system like TOI-6894b does not merely add one more entry to the endless richness of exoplanet catalogs. It shifts the emotional texture of the category. Red dwarfs stop feeling like stars that mostly host modest outcomes. They become places where our confidence has to stay provisional. And the further we follow that thought, the more disorienting it becomes. Because red dwarfs are not occasional decorations scattered across the Milky Way. They are the background population, the long-burning, low-key stars that may outlive brighter stars by absurd stretches of time. They are, in a sense, the galaxy's default setting, which means that if giant planets can arise around them through routes we have underestimated, then part of what is at stake here is not a correction to some obscure corner of astronomy. It is a correction to how we imagine the most common planetary neighborhoods in the galaxy. That possibility changes the scale of the discovery without changing a single fact about the object itself. The star remains small, the orbit remains short, the planet remains what it is. What expands is the implication. Because an anomaly at the margin is one thing, an anomaly attached to the dominant stellar population is another. Once that clicks into place, the system stops looking like a freak accident and starts looking like a question pointed at the census of the Milky Way itself. And a census problem in astronomy is never just about counting. It is about proportion, expectation, and the stories we tell ourselves about what the galaxy is mostly made of. If we misunderstand the planetary possibilities around the most common stars, then we are not slightly off. We are skewed where it matters most. It helps, at this point, to come back to what a red dwarf actually is, because the phrase can drift into abstraction. The sun has taught us a certain emotional grammar for starlight. A star is bright, central, dominating, the obvious monarch of its system. A red dwarf breaks that image. These stars are smaller, cooler, dimmer, and in some cases so restrained that if one replaced the sun, the sky as we know it would be radically altered. Daylight would not have the same authority. The source of heat and light would feel less like a blazing presence and more like a reduced ember holding on for an extraordinary length of time. That reduction in brightness is part of why they are easy to neglect in the imagination, even while they dominate the actual stellar population. Our intuitions are drawn to the loud and the luminous. The Milky Way is not. So when a gas giant turns up around a star, like TOI-6894, the discovery carries a double insult to instinct. First, the star is not the kind most people picture when they hear the word star. Second, the planet is not the kind of outcome many researchers expected such a small system to produce. The system is ordinary by category and unsettling by composition. That is a very fertile combination in science. It means the surprise is hiding in plain sight. The older, simpler story of giant planet formation worked because it was not arbitrary. You need enough solid material to build a core. You need that to happen before the gas disk thins away. Around lower mass stars, disks tend to be lighter. That should lower the odds of making a giant planet. Even today, that basic expectation has not been thrown out. The issue is not that the logic was foolish. The issue is that nature seems willing to produce outcomes near or beyond the edge of what that logic encouraged us to expect. And there is an important emotional difference between those two statements. One says the science was worthless. The other says the science was useful, but reality has more room in it than the shorthand version allowed. Most mature discoveries feel like that. They do not replace ignorance with certainty. They replace a clean picture with a truer, messier one. There is something deeply human in how much that unsettles us. We love thresholds. We love categories. We love being able to say that one environment makes one family of things, while another environment makes another. It gives the universe a zoning map. Rocky planets here, gas giants there, bright stars with large entourages, small stars with smaller ambitions. The problem is not that those patterns are empty. The problem is that once a pattern starts helping us, we begin to lean on it emotionally, not just scientifically. Then a system like this arrives and reminds us that the cosmos does not care what helped us feel oriented. TOI-6894b circles its host in a little over 3 days. That is an astonishingly short year, but because the star is dimmer and cooler than the sun, it is not enough to simply import our usual language from hot Jupiters around sun-like stars and assume the same story. Context matters. A close orbit around a faint red dwarf is not the same physical setting as a close orbit around a larger, brighter star. This is another place where common language tries to flatten what matters. Close sounds universal. It isn't. In astronomy, the meaning of distance changes with the light and heat of the thing you are orbiting. That subtlety is easy to lose in a title like this, but it belongs inside the deeper story, because it shows what kind of discovery this really is. Not just a strange object, but a strange object embedded in a system where nearly every familiar shortcut threatens to mislead us. Small star does not mean simple outcome. Close orbit does not mean familiar category. Giant planet does not automatically mean the same formation story we tell elsewhere. Every descriptive term needs more care than usual. That is often a sign we are dealing with something genuinely valuable. One of the quiet powers of exoplanet science is that it has repeatedly humiliated any assumption that our own solar system is a good template for what planetary systems are supposed to look like. Before the first wave of exoplanet discoveries, it was easy to let our arrangement feel typical. Small, rocky worlds inside, gas giants farther out, broad spacing, long orbital periods for the largest planets, familiar order. Then planets started turning up in places and combinations that made our old intuition look parochial. Massive worlds hugging their stars, densities that barely seemed real, orbital resonances of eerie precision, systems so compact that if they were dropped into our own solar system, several planets would sit closer to the Sun than Mercury. The more planets we found, the less secure the word normal became. That wider history matters here because TOI-6894b is not shocking in a vacuum. It lands in a field already trained, by painful experience, to distrust any strong instinct about what planets should prefer. And still it stands out. That is part of what gives the discovery its force. Exoplanet science is no longer in its innocent phase. Astronomers have already lived through multiple rounds of surprise. For a system to keep feeling genuinely awkward now, it has to press against expectations that have already been made more flexible, which means the discomfort is earned. If this were the only such case, it would still be intriguing, but there is a reason people sometimes mention other red dwarf giant planets in the same breath. A system like TOI-6894b had already raised eyebrows by putting a giant planet around a very small star. Each case is its own object, its own history, its own problem. No one discovery automatically explains another, but repetition changes the mood. It is the difference between hearing one strange story from a distant town and realizing that similar stories keep surfacing in different places. At some point, the issue stops being whether one report is odd. The issue becomes whether the world is arranged differently than you thought. That is where astronomy becomes almost philosophical without losing its footing in data. Because the word anomaly sounds more decisive than it really is. An anomaly can mean a genuine outlier. It can also mean the first visible edge of a larger population we have not sampled well enough yet. Early in any discovery cycle, those two possibilities are difficult to separate. We see the strange object first. Only later do we learn whether it was rare, hidden, or merely waiting for our instruments to get good enough. And our instruments matter here more than they often get credit for. A huge amount of what we call the universe is actually the universe filtered through detectability. We do not discover planets in proportion to their abundance alone. We discover them in proportion to abundance, geometry, brightness, timing, instrument sensitivity, observation strategy, and luck. A transit has to line up. A signal has to be clear enough. A star has to be monitored long enough. Follow-up observations have to happen. Even our surprises arrive through a selection process. So when a giant planet turns up around a tiny star, one of the live questions is not only, how did this form, but also, how many more of these have we been missing? Maybe very few, maybe enough to matter statistically, maybe enough to force a real recalibration of formation models around low-mass stars. That uncertainty is not a weakness in the story. It is part of the forward pull. The discovery does not close the case. It opens the room. And once that room opens, the old image of red dwarfs begins to change. They stop feeling like modest systems that mainly produce modest architecture. They become quieter neighborhoods where the zoning laws might have been misunderstood. A house appears where there should have been a shed. Then another town reports something similar. You do not yet know whether there is a pattern, but you know the old map can no longer be trusted in the same way. That is how science usually changes on the inside. Not through one dramatic sentence, but through a slow corrosion of certainty. First, the rule acquires exceptions. Then the exceptions start looking less decorative. Then the language around the rule becomes more careful. What once sounded absolute becomes statistical. What once sounded clean becomes conditional. Eventually, the field reaches a new equilibrium, and future students grow up inside a picture that seems perfectly natural to them, not realizing how strange it felt when it first arrived. We may be somewhere in that process now, with low-mass stars and giant planets. Not at the end of it, not yet, but far enough along that the older confidence can no longer carry the same weight. And there is something quietly beautiful in that, because it means the galaxy is still able to surprise us in its most common places, not just its spectacular ones. A faint red dwarf, after all, does not look like the kind of object that should force a reconsideration of planetary abundance and formation pathways. It looks like background. It looks like the sort of star the human mind would file under minor. But that is one of the oldest mistakes we make when looking at the universe. We confuse brightness with significance. We assume the louder setting is the more important one. The Milky Way has never promised that. In fact, one of the great recurring lessons of astronomy is that the background is often where the real scale is hiding. Our own senses are built to notice contrast, not prevalence. We remember the bright thing in the room. The galaxy keeps reminding us that the room is mostly made of dimmer things that last longer, outnumber the bright ones, and may be carrying much more of the story than our instincts would ever grant them. Red dwarfs are a perfect example of that mismatch between intuition and inventory. They do not dominate human culture the way a star like the Sun does, because no one on Earth grew up under a red dwarf sky. We are calibrated to one stellar environment and then tempted to universalize it. That is a very ordinary human error. We treat the local as representative until evidence becomes annoying enough to stop us. A world like TOI-6894b is exactly that kind of annoyance, productive annoyance, a refusal by reality to stay inside the neat version. To understand why this matters so much, it helps to think less about the single planet for a moment and more about the architecture of confidence. Planet formation theory is not one monolithic block. It is layers of evidence, simulations, assumptions about disks, timescales, migration, chemistry, and collision histories, all held together by the fact that many of its broad predictions really do line up with what we see. That is why a strange system does not just get brushed aside as a curiosity. It presses on a structure that has earned trust. The stronger the structure, the more informative the pressure. If planet formation were chaos all the way down, this discovery would not feel special. It would just be one more random arrangement. It feels special because the field has spent decades learning that planetary systems are not random. Certain outcomes cluster. Certain kinds of stars tend to host certain kinds of planets more often than others. Metal-rich stars, for example, show stronger links to giant planet occurrence. Disk properties matter. Mass matters. Environment matters. The universe has habits. But habits are not vows. That is where the real tension lives. We are not dealing with a universe that has become incomprehensible. We are dealing with one that remains intelligible while refusing to become fully obedient to our simplifications. A small star usually means a smaller budget. A smaller budget usually means lower odds for a giant planet. Yet here one is. The significance lies in that yet. That word carries a lot. It keeps us from slipping into either of the lazy extremes. One extreme says the planet is impossible and science is broken. The other says exceptions happen, so nothing matters. Neither of those reactions is serious. The serious response is narrower and more interesting. Something in the formation story for at least some low-mass stars is more permissive, more efficient, or more varied than the clean version implied. And when you start thinking in those terms, the star system becomes less like a contradiction and more like a clue. Clues in astronomy are often painfully indirect. We do not watch the planet form. We do not see the early disk in this system and then fast forward the movie. We inherit the outcome after the building site has long since vanished. The original gas is gone. The dust is gone. The collisions are over. What remains is a mature arrangement, and from that arrangement we try to work backward. It is forensic science, conducted at stellar distances and planetary timescales. That forensic quality changes the emotional tone of the whole discovery. This is not a spectacle, it is a reconstruction. We are standing at the end of a process we never witnessed, holding measurements and asking what sequence could have produced them. That is part of why astronomy can feel so strangely intimate, even when it deals with unimaginable distances. It is not only about scale, it is about inference, about the mind reaching across emptiness and trying to rebuild an unseen history from faint traces. TOI-6894b invites exactly that kind of reconstruction. Perhaps the system started with a disk unusually massive for such a small star. Perhaps the solids in that disk concentrated efficiently enough to create a core faster than average. Perhaps migration later moved the planet inward after it formed farther from the star, where conditions were better for gathering gas. Perhaps more than one of those things is true. Each possibility is plausible in principle. The discomfort comes from not yet knowing which path nature took, and from realizing that the path might not be as rare as we once hoped. The phrase "once hoped" is doing real work there. Scientists do not merely collect explanations, they rely on them. There is a practical comfort in a model that lets you sort outcomes with reasonable confidence. It helps determine what surveys to run, which stars to prioritize, which detections would count as routine, and which would count as strange. A field organizes itself around what it expects to find. When the findings start to blur those expectations, the field becomes more honest, but also more exposed. And that exposure is one of the healthiest things science can experience. It is easy, from the outside, to imagine astronomy as a discipline built from certainty, because its language can sound so clean in finished form. Orbital period, radius, mass, host star, transit depth. But under those terms is a much more vulnerable activity, the attempt to make reality legible without forcing it into a shape we find emotionally satisfying. Every strange exoplanet is a test of that discipline. Some merely widen the range. Others show that a comfortable narrative has become too blunt. This one leans in the second direction. The star itself sharpens that feeling. TOI-6894 is not just smaller than the Sun. It sits in a regime where, for a long time, giant planets were expected to be especially scarce. Not absent in some metaphysical sense, but scarce enough that finding one around such a low-mass star would immediately feel like a system asking for extra explanation. The host is not some middling case that leaves room for casual shrugging. It is a tiny red dwarf pressing close to the lower stellar mass range, where these questions become especially pointed. So the discovery arrives with an almost architectural awkwardness. The foundation looks too light for the structure it is carrying. That image is worth holding because it captures the emotional truth without distorting the science. The planet does not violate gravity. The star does not fail to be a star. Nothing supernatural has happened. It is just that the final arrangement feels like a house whose visible support does not match our expectations of what such a structure requires. We know there must be an explanation. The puzzle is whether the support is hidden, whether the building process was unusual, or whether our rules of thumb about support were too rigid all along. This is where some of the deeper philosophical texture begins to surface. Human beings are often much more comfortable with visible causes than distributed ones. We like a clean link between the scale of the source and the scale of the outcome. Small in, small out. Big in, big out. That instinct serves us well in ordinary life. It fails more often in complex systems. Ecosystems, economies, climates, civilizations, and planetary nurseries all produce outcomes that can look disproportionate when too many quiet processes stack together in the same direction. A giant planet around a tiny star has that flavor. It feels disproportionate, which may be precisely why it is so revealing. Because the more we learn about the universe, the more often it turns out that ordinary-looking settings can hide nonlinear stories. A dim star can have an unexpectedly rich early disk. A small difference in solid concentration can alter the speed of core growth. Migration can rearrange the final layout, enough to make origin and present appearance diverge. None of that guarantees this system's history, but it does point toward a larger reality. Planetary systems are not assembled by a single clean lever. They are shaped by a stack of interacting processes, some of which may only occasionally align to produce something that looks impossible from the outside. And occasional alignment is enough to matter if the stage is large enough. That is the part the Milky Way keeps forcing on us. Even rare outcomes become significant in a galaxy with hundreds of billions of stars. A low-probability architecture is still a real architecture if the sample size is huge. If red dwarfs make up most stars, then even uncommon giant planets around them could represent an enormous number of worlds in total. Suddenly the phrase "unlikely system" stops sounding small. Unlikely multiplied by the galaxy is still a population. That is a difficult thing for the human mind to feel properly. We are good at noticing frequency in rooms, cities, maybe nations. We are not built to carry the arithmetic of the Milky Way in our nervous systems. Astronomy keeps forcing that gap open. A thing can be rare and still happen millions or billions of times. A thing can strain theory and still be astrophysically abundant in absolute terms. The scale of the stage changes the meaning of every probability placed upon it. So the story is no longer just about whether one giant planet should have formed around one tiny star. It becomes about what kind of hidden demographic the galaxy might contain, if even a narrow pathway for such planets exists. A quiet background population of stars could be carrying a quietly surprising background population of worlds. And once that possibility takes hold, the night sky stops feeling quite so sordid. It starts to feel less like a tidy atlas, and more like a landscape whose most familiar districts were only ever familiar because we had not looked closely enough. That is one of the odd emotional reversals astronomy produces again and again. The spectacular objects draw us in, but very often it is the supposedly ordinary setting that quietly rearranges our sense of reality. A red dwarf is ordinary in exactly that dangerous way. It is ordinary statistically, not imaginatively. We can say with confidence that the galaxy is full of them, that many will outlive brighter stars by unimaginable lengths of time, that they are a dominant feature of the Milky Way's true stellar inventory, and yet very few people carry them around in the mind with any real vividness. They remain background objects, abstract and interchangeable, until a system like this suddenly gives one of them personality. Not because the star itself is dramatic in the usual sense. It is dramatic because of the mismatch it permits. There is a useful distinction here between surprise and contradiction. Surprise means the system falls outside our preferred expectations. Contradiction would mean it cannot be reconciled with the physical principles we trust. TOI-6894b lives firmly in the first category. Nothing about it asks us to abandon gravity, thermodynamics, orbital mechanics, or the broad idea that planets grow from disks around young stars. The disturbance is subtler than that, and therefore more interesting. It asks whether the pathways to giant planet formation around small stars are more open than we assumed, whether the tails of the probability distribution have been underappreciated, or whether our observations of disks and outcomes have encouraged a false sense of closure. Closure is often the thing that discoveries like this punish. We take a field that is still growing, still noisy, still haunted by incomplete samples, and we begin speaking about it as though the main architecture is settled. Not because we are foolish, but because working science needs provisional stability. You cannot ask good questions if everything remains equally unconstrained. So theories acquire a useful firmness. Over time, that firmness can begin to feel like a boundary in nature, rather than a current boundary in our description of nature. Then the universe places a giant planet around a tiny star and reminds us that our neatness is not one of its obligations. That reminder lands even harder because the planet is not merely large in some abstract catalog sense. Its physical character matters. TOI-6894b is roughly Saturn-sized in radius and relatively low in mass compared with Jupiter, which means it belongs to that class of gas giants that can seem oddly inflated, large in appearance without the crushing heft many people associate with the phrase giant planet. That nuance matters because it gives the system a more textured reality. This is not simply a dense cannonball circling a frail host. It is a substantial gaseous world, extended, almost soft in conceptual outline compared with rock or metal, yet still far too grand an outcome for the budget many people thought such a star could easily support. That is one of the quiet pleasures of astronomy when it is told honestly. The objects are never just symbols for an idea. They are specific things. This planet has a size, a mass, an orbit, a relationship with starlight, an atmospheric structure that future observations may continue to probe. The theory is under pressure because the world is concrete, and concrete worlds have a way of pulling speculation back toward humility. We can propose histories for TOI-6894b, but we cannot simply choose the most elegant one because it feels satisfying. Nature may have taken a clumsier path. It may have taken a path that only works under a narrow combination of conditions. It may have done something common in low-mass systems that we have simply not observed enough yet. The discovery does not grant us the right to invent a convenient rescue story. It grants us the duty to become more careful. That carefulness is one of the reasons astronomy can be so emotionally compelling without becoming loud. The drama is not that people are yelling. The drama is that a real object exists first. An explanation has to catch up. The sky gets the first move. The transit itself embodies that asymmetry beautifully. Long before anyone had a satisfying narrative for the planet's existence, there was already the repeated dimming in the star's light, the stubborn periodic signal saying, in effect, something is there. Not something in the imagination, not something we would like to be true, something measurable, something that returns on schedule. There is a humility in being corrected by a pattern of light. It is hard to overstate how strange that is from a human point of view. On one planet, around one middling star, a species evolved that can sit in the dark, collect photons from a small red dwarf many light years away. Notice that the brightness drops by a small fraction every few days, and from that infer the existence of a giant world that theory had not wanted to place there comfortably. We talk about instrumentation and analysis, and of course those things matter, but beneath them is a more fragile fact. Consciousness has become capable of being surprised at distance. That alone makes these discoveries feel larger than their technical wording. And then there is the question of whether TOI-6894b is rare in the strong sense or only rare in the temporary sense. Those are not the same thing. A thing can seem rare because it seldom happens. It can also seem rare because it is difficult to detect, easy to misclassify, or simply because the survey depth has not caught up to the size of the sky. Exoplanet history is full of cases where a category felt unusual until the tools improved, at which point the category turned out not to be common exactly, but common enough to change the way we thought about planets in general. That historical memory is important here. We have already watched odd planets become part of the furniture of the cosmos. Hot Jupiters were once startling. Ultra-short period rocky planets would have sounded strange in an earlier era. Super-Earths are abundant, even though our own solar system does not offer a clean analog. Compact multi-planet systems seemed peculiar until they began showing up with enough regularity to feel like one more way of arranging a solar system. Each time, the same deeper lesson returned. The local picture had been too narrow. That does not mean every anomaly becomes normal. Some objects do remain genuinely unusual, but the mere fact that something strains intuition is no guarantee that it occupies only the farthest statistical fringe. Sometimes, what looks improbable is simply what our instincts were not trained to expect. Small stars are a powerful place for that lesson, because they reveal how much we confuse everyday visibility with cosmic centrality. We live beside one star that dominates our daylight, our climate, our biological rhythms, our old myths, our vocabulary of warmth and brightness. It is almost impossible not to treat that star as the default emotional model of a star. But the galaxy has other defaults. Most stars are smaller, dimmer, slower burning, less flamboyant. If those stars host more architectural variety than we assumed, then the true ordinary may be stranger than the version of ordinary we inherited from our own neighborhood. That thought has consequences far beyond one planet. It reaches into questions about planetary demographics, atmospheric evolution, orbital migration, and even long-term habitability across the galaxy. Not because every giant planet around a red dwarf directly affects those topics in the same way, but because every such system changes the prior assumptions with which we approach low-mass stars. It tells us to ask broader questions. It tells us not to reduce these stars to one expected menu of outcomes. And science advances partly by widening menus. There is also something wonderfully unsentimental about the way this discovery sharpens our sense of the word normal. We use that word as though nature were built around the comfort of averages. But averages are summaries, not sovereigns. The most common stars can still host uncommon histories. A common environment can still produce outcomes that feel, from the inside of our models, almost indecently extravagant. A poor-looking construction site can still surprise you with what it somehow managed to build. That image keeps returning because it is so hard to escape. A small account, an enormous purchase. A workshop with too little steel somehow launching a ship. A star that looks like it should produce modest planets now carrying a giant one around every few days, as if none of our psychological bookkeeping mattered in the first place. And perhaps that is the most unsettling part. The universe is not only larger than our categories, it is often calmer than they are. The planet simply exists. It does not announce itself as scandal. The scandal is ours, because we had mistaken a strong expectation for a quiet law of reality. And once you notice that, the tone of the whole story changes. It stops being a tale about the universe doing something flamboyant, and becomes a tale about us discovering where our own confidence had become too smooth. The planet is not outrageous in temperament, it is outrageous in placement. That distinction is important, because it keeps the wonder honest. We are not looking at fantasy. We are looking at an arrangement of matter that forces a revision in emphasis. Revisions in emphasis can sound small until you realize how much of science depends on emphasis. It is one thing to say giant planets around very low-mass stars are unlikely. It is another to say they are so disfavored that each new case deserves serious theoretical attention. Those sentences are close enough to share a vocabulary and far enough apart to change a field's posture. The first encourages background confidence. The second keeps the door open. TOI-6894b pushes us toward the second. There is a temptation, whenever a discovery strains expectation, to immediately search for the one fix that will restore the old comfort. Perhaps the disk was just unusually massive. Perhaps the planet formed farther out and migrated inward. Perhaps some instability in the disk helped matter clump more efficiently. Perhaps the system belongs to a rare subclass we had not accounted for cleanly. Those are all reasonable possibilities. But notice what happens emotionally when we reach for them too fast. We are not only explaining the planet, we are trying to protect a familiar worldview from becoming more permeable than we like. Sometimes the repair is real, sometimes the repair is premature. Migration, for example, is often invoked because it is a genuine part of planetary evolution. Worlds do not always stay where they formed. Gravitational interactions with the disk or with other bodies can move them inward or outward over time. A giant planet close to its star does not have to have formed there. But migration is not a free pass. It explains location, not existence. Before a planet can move inward, it still has to become a giant planet somewhere. And around a very low-mass star, that original formation problem remains the heart of the tension. That is why the discovery keeps its teeth, even after the first round of possible explanations is placed on the table. None of them feels absurd. None of them is sufficient by mere mention. The real question is not whether we can imagine a path. It is whether those paths occur often enough, efficiently enough, and under plausible enough conditions to produce the worlds we are beginning to observe. This is where the story becomes larger than a single system. A lone oddity can be accommodated with a special case. Science can always say, in effect, perhaps this was one of those unusual histories that nature occasionally allows. But the more examples appear, the less satisfying that posture becomes. Special pleading has a shelf life. After that, what looked like an exception starts looking like undercounted possibility. And the galaxy is large enough that undercounted possibility can hide for a very long time. That scale matters in a way that is easy to say and hard to feel. When astronomers speak about occurrence rates, probabilities, and distributions, they are often working with percentages that sound modest in ordinary language. A few percent here, less than 1% there. In everyday life, those numbers feel like edges, not centers. But the Milky Way is not everyday life. When the stage contains hundreds of billions of stars, even a sliver of probability becomes a population. A configuration that is statistically uncommon can still represent more worlds than the human mind can picture with any sincerity. So if giant planets around stars like TOI-6894 are merely rare, that may still mean they are cosmically consequential. And if they are less rare than expected, the consequence grows again. Either way, the discovery asks us to stop confusing not the dominant trend with not worth restructuring our picture around. That confusion is common far beyond astronomy. We have a habit of treating the average outcome as the morally proper one, the one reality ought to stick with. In truth, averages are bookkeeping devices. They are useful compressions of a messier world. They tell us something real, but never the whole thing. The danger comes when we start granting them emotional authority. Then anything outside the average begins to feel like an insult. TOI-6894b carries exactly that kind of insult. Not because the science was foolish, but because human beings are so quick to turn well-supported tendencies into mental zoning laws. Around these stars, we say to ourselves, certain things belong and certain things do not. Then the galaxy builds one anyway. A quiet star, a substantial world, a short orbit, a signal in the light. And suddenly, the zoning office is gone. That image may sound playful, but there is a serious principle inside it. Complex systems often produce outcomes that are entirely legal under the deeper physics, while still violating the cleaner, higher-level expectations we build for convenience. Climate does this. Biology does this. Markets do this. History does this. Planet formation appears to do it too. The lower-level rules remain intact, while the higher-level patterns we trusted turn out to be more permeable than they seemed. And permeability changes how our reality feels. Before discoveries like this, it is easy to picture the galaxy as a place where broad stellar categories map neatly onto broad planetary categories. Small, cool stars mostly host one kind of architecture. Larger stars host another. Yes, there are edge cases, but the broad emotional geometry remains orderly. After enough edge cases, that feeling evaporates. The galaxy does not become chaotic. It becomes more alive than orderly, more permissive, more improvisational within constraint. That phrase matters. Improvisational within constraint. Nature is not doing anything it likes. It is operating through gravity, chemistry, radiation, angular momentum, collision, dissipation, timing. The freedom is not lawlessness. It is combinatorial richness. Given enough disks, enough stars, enough slight differences in metallicity, density, turbulence, migration history, and early environment, the range of viable outcomes becomes wider than any tidy sentence wants to admit, which means that even the commonest stars may host stories our shorthand was not built to hold. There is a gentle irony in that. Red dwarfs were already important in exoplanet science because their small size can make transiting planets easier to detect in some cases. They are quiet stars that help reveal quiet measurements. Yet the more we study them, the less quiet their implications become. They were supposed to offer some of the clearest routes to understanding small planets around abundant stars. Now they are also helping expose where our assumptions about giant planets may have been too cramped. The same category of star is giving us simplicity in one domain and complication in another. That is often how reality behaves. It does not sort itself into pedagogically satisfying roles. The phrase, "around that star," keeps gaining force because the word that is doing so much work. If TOI-6894b orbited a larger, more massive star, it would still be an exoplanet worth study, but it would not carry the same philosophical charge. Here, the host is the entire point. The host is what transforms a world from interesting to revealing. The host is what turns measurement into argument. And perhaps that is one of the deepest lessons hidden in this kind of discovery. Context is not decoration. In astronomy, as in life, the same object can mean very different things depending on what surrounds it. A gas giant is one thing in a rich, sun-like system, and another in the company of a tiny red dwarf. The object remains itself. Our interpretation changes because the environment changes what counts as ordinary. The longer we stay with that idea, the more the title stops sounding like a sensational claim and starts sounding like a diagnosis of our own mental habits. A planet that shouldn't exist around that star is really a planet that shouldn't exist around that star, according to the version of the universe we had made emotionally comfortable for ourselves. And now that comfort is beginning to look expensive. Because comfort in science, when it lasts too long, can quietly turn into blindness. Not blindness in the dramatic sense, not a failure to look, a subtler thing, a tendency to stop feeling the provisional nature of even our best explanations. The field keeps the proper caveats on paper, of course. Astronomers know better than anyone that models are models, that populations are incomplete, that the sky is always larger than the survey. But human beings do not live by caveats emotionally. We live by the shape of the story we have repeated enough times to trust. For a while, the story was that very low-mass stars were not the natural homes of giant planets, not impossible homes, not forbidden homes, just strongly disfavored ones. That was a sensible story. It was rooted in disk mass, formation timescales, and the practical economics of planetary construction. Yet what discoveries like TOI-6894b reveal is that sensible stories can still become too small for the worlds they are supposed to contain. It is worth feeling the physical problem again, because the whole script turns on it. A young star forms inside a cloud. Around it, a disk of gas and dust spins out. From that disk, planets must somehow emerge. In the case of a giant planet, the process has to move with real urgency. A core has to grow to substantial size, while the gas is still present. Too slow, and the gas reservoir vanishes before the world can bulk up. Around a bigger star with a richer disk, there is at least more to work with. Around a tiny red dwarf, the budget looks lean from the start. Less raw material, less apparent room for extravagance. And yet extravagance appears. A world almost the size of Saturn ends up circling a star that feels, in comparison, stripped to essentials. Not dead, not marginal, just modest. The visual imbalance keeps mattering because it gives the theory somewhere to land in the imagination. We are not dealing with an argument that lives only in specialist language. We are dealing with a mismatch you can actually carry in the mind. A small lamp, a huge ornament moving around it. A workshop with too little steel somehow launching a ship. That does not prove any particular formation pathway. It does something almost more important. It keeps the problem from dissolving into jargon. And the problem becomes sharper when we remember that the host star is not some private curiosity known only to a few specialists. It belongs to the galaxy's dominant stellar class. If a massive blue star hosts something strange, we can instinctively file the case under rarity. If a common red dwarf hosts something theory had learned to treat as scarce, then the strangeness attaches itself to the ordinary fabric of the Milky Way. It stops feeling quarantined. This is where the discovery begins to exert pressure beyond planetary science itself. It becomes a lesson in how reality hides complexity inside what looks commonplace. Human beings do this badly. We assume the familiar category is the well-understood category. We assume the common thing is simple because it is common. But commonness only tells us about frequency. It says nothing about how much hidden variety the category can contain. Red dwarfs are common. Their possible planetary histories may be less simple than that label encouraged us to feel. There is a strange dignity in that. The galaxy's quietest stars are not merely background infrastructure. They are sites of unanswered questions. They may even be sites where the universe is still withholding some of its biggest demographic secrets. Not because each individual star is spectacular, but because when a category dominates the sample, even subtle misunderstandings can scale into major distortions of the whole picture. This is one of the hardest things to internalize about astronomy. Scale changes the moral weight of error. If we misunderstand a rare type of object, we are wrong in a narrow corridor. If we misunderstand the most common stars in the galaxy, we are wrong in the main hall. That is why discoveries like TOI-6894b feel larger than their immediate facts. And the immediate facts are already strange enough. The planet whips around its star in a little over 3 days. That short orbital period gives the system a compactness that can be difficult to feel properly. A year there is over almost as soon as we have named it. But compactness, again, is context-dependent. Around a dim red dwarf, close in does not map neatly onto the emotional meaning it would have around a brighter star. The whole system is constantly trying to trick us into importing familiar categories from elsewhere. That is part of its power. It exposes how often our understanding depends on analogies that are only partly true. Even the word giant can mislead if we hear it too lazily. Giant in exoplanet science covers a lot of physical personalities. TOI-6894b is not simply a duplicate of Jupiter parked in an absurd place. It is lower in mass, extended in size, a gaseous world whose structure matters. This is not just about bulk, it is about what kind of bulk. A diffuse large planet tells a different physical story than a compact heavy one. The discovery gains texture the moment we let the object remain specific instead of flattening it into an emblem. Specificity is one of the main defenses against bad wonder. Bad wonder inflates everything into a generic miracle. Good wonder makes the thing itself clearer. So the clearer this planet becomes, the more unsettling its existence is. Not because it breaks the universe, but because it occupies a space where our simplified version of the universe had started to sound too complete. It is one thing to know in theory that low-mass stars might occasionally surprise us. It is another to hold a measured, named, orbiting world in mind, and realize the surprise is already sitting there in the data. And data, in this story, has an almost moral quality. It does not argue in the way people do. It persists, a recurring dimming, a measured radius, a constrained mass, a small host star. Again and again, the evidence says the same thing. Whatever ease we had in imagining that giant planets belong elsewhere, nature has not agreed to preserve it for us. That steady correction is part of what makes astronomy so calming when it is good. The field is full of large emotions, but the method itself is patient. Nobody needs to shout when the photons keep arriving. Nobody needs to dramatize uncertainty when the object is already there, and the real question is simply what sequence of events could have made it. The sky applies its pressure quietly, which is also why the story has more staying power than a headline. A headline gives you the scandal in a sentence. A real narration stays long enough to show why the scandal remains after the novelty wears off. If anything, it grows. At first we hear, "planet that shouldn't exist," and translate it into a vague sense of surprise. Then we start feeling the actual structure of the problem. Small star means small disk, on average. Small disk means less material and tighter timing for giant planet formation. Red dwarfs dominate the galaxy. Therefore, any loosening of those expectations affects not only one object, but a potentially enormous population base. The title keeps paying off because the phrase around that star never stops deepening. And then another layer appears. Because if low-mass stars can sometimes host giant planets, those planets may influence the rest of their systems in ways that matter. Giant planets are not passive ornaments. They can reshape dynamical histories, alter orbital architecture, scatter smaller bodies, affect migration patterns, and change what other planets in the system experience over time. So, a giant planet around a red dwarf is not simply one more occupant. It may be part of a different story for the whole neighborhood. That opens the room further. Now the discovery is no longer just about a mismatch between star and planet. It becomes a possible sign that some red dwarf systems have histories more structurally complex than we imagined. Their calm exterior may hide a rougher past. Their present layout may be the result of earlier motion, competition, rearrangement. Once a giant planet is allowed into the picture, the system stops feeling modest in the old way. This is another common mistake in human thought. We treat visible quiet as evidence of simple history, but many stable-looking systems are the frozen result of violent or improbable sequences that no longer announce themselves directly. A mountain range can look serene and still be the record of immense pressure. A civilization can look orderly and still rest on centuries of contingency. A mature planetary system can look clean and still preserve the outcome of migrations, collisions, and narrow timing windows. The calm comes later. The complexity was always there. TOI-6894b carries some of that feeling. We see the finished arrangement. Somewhere behind it is a history that our current explanations do not yet hold with full confidence. The planet's orbit is present tense. The real mystery is past tense. And that may be the reason discoveries like this linger in the mind more than cleaner cases do. They are not only objects, they are unfinished explanations. They leave a live edge in thought. You can close the browser, go outside, look at an ordinary evening sky, and still feel that one faint star somewhere is carrying a world that our most comfortable planetary story had not properly made room for. And once a fact begins to follow you around like that, it has already done more than inform you. It has changed the emotional weight of a category. A red dwarf is no longer just a red dwarf. It becomes a place where one question has failed to stay closed. The star itself has not changed, of course. It remains small, cool, dim, and physically unoffended by our confusion. But our relationship to that class of stars changes. We stop seeing them as simple placeholders in the galaxy's inventory, and start seeing them as long-lived laboratories with more variance than the comfortable version of the story had room for. That shift matters because astronomy is full of categories that feel settled, mainly because language has made them feel settled. Say, small star, often enough, and the phrase begins to drag a whole shadow of assumptions behind it. Small means limited. Limited means fewer options. Fewer options means fewer surprises. It sounds clean. It even sounds rational. But nature is constantly showing us that limited inputs can still produce disproportionate outcomes when multiple processes reinforce each other in the same direction. We know this in other parts of life. A small political decision can ramify into a vast historical consequence. A tiny genetic change can alter an organism's whole future. A quiet accounting trick can reshape an economy. Complex systems are full of thresholds, feedbacks, timing windows, and hidden leverage. Planet formation is not exempt. A slightly richer disk, a slightly faster phase of core growth, a slightly more favorable distribution of solids, a migration history that happens to avoid catastrophe rather than invite it. Stack enough of those advantages together, and the final result can look much grander than the initial conditions seem to warrant. That may be what a system like TOI-6894 is telling us. Not that physics has been suspended, but that the route from starting materials to final architecture contains more hidden leverage than our shorthand had allowed itself to acknowledge. The shorthand was understandable. Most of us do not live at a level where we can feel distributions and tales of probability with any honesty. We need simplifications. Science needs them too. Without simplification, there is no model, only noise. But simplifications age. They become smoother as they are repeated, more confident as they are taught, more emotionally solid as they prove broadly useful. Eventually, they start sounding like the underlying reality itself. Then, some dim red star with a giant companion turns up in the data, and all at once, you can hear the simplification rattling around inside the sentence. That rattle is one of the most valuable sounds in science. It means the map has begun to confess that it is a map. And what a peculiar map this has become. For years, the exoplanet revolution has been teaching us that planetary systems are more various than our own neighborhood suggested. That lesson alone was already enough to humble any attempt at neatness. Yet even inside that broader humility, new local confidence is formed. We learn to expect certain frequencies around certain kinds of stars. We refined the language. We became more quantitative. We moved from astonishment at the sheer existence of exoplanets to subtler questions of demographics and formation channels. The field matured. Then maturity produced a new layer of assumptions. That is almost inevitable. Knowledge does not eliminate surprise. It changes where surprise lives. In the early days, the shock was that planets existed in bizarre places at all. Now the shock is more discriminating. It lives in the details. This host mass, this radius, this orbit, this metallicity, this population trend, this exception that keeps failing to behave like a decorative outlier. Surprise moves from the headline level to the structural level. TOI-6894b belongs to that more mature form of surprise. The planet itself is not astonishing because we have never seen a gas giant before. It is astonishing because we have seen enough to know why this pairing is awkward. A discovery like this does not arrive into innocence. It arrives into a field that has already learned caution, and still, it manages to press on a nerve. That is usually a sign that the discovery deserves to last. There is also a quieter human reason it lasts. The system forces us to confront how much of our sense of order depends on invisible proportionality. We like outcomes that match their origins. Large stars, hosting large planetary systems, feel emotionally proportional. Small stars, hosting smaller-scale arrangements, feel proportional too. When those expectations are disturbed, the discomfort goes beyond the science. It touches our deeper appetite for fit, for symmetry, for a universe that feels as though it respects our intuition about resource and result. But the universe does not exist to respect that intuition. It exists to instantiate whatever combinations the underlying processes allow. That sounds abstract until you picture the actual scene. A star with about a fifth of the sun's mass. A giant world crossing in front of it every few days. A measurable dimming in the light. An object almost Saturn-sized, orbiting a host that would have seemed, under the easier version of the theory, too slight to produce such a thing comfortably. Not impossible, just too slight to feel good about. The whole case turns on that feeling. Because feeling is where the theory had quietly settled into confidence. We should stay with the material side of the story here, because this is where the title keeps earning itself. Giant planets are not merely big rocks. They are worlds whose existence implies an early triumph over time. To become gas giants, they need access to gas, while the disk is still gas-rich. That means a core has to emerge and begin pulling in that envelope before the opportunity disappears. It is a race against dissipation. Around low-mass stars, the race was thought to be especially unforgiving. There is simply less slack in the budget. And TOI-6894b looks like the record of a race somebody expected to lose. That does not mean the race is unwinnable. It means the finish line has become less exclusive than some versions of the model encouraged us to believe. Which brings us back to the larger implication. What else have we mistaken for exclusive simply because the prevailing route looked narrow? This is one reason repeated detections matter so much. A single case can always be treated as an astrophysical oddity, a narrow tunnel that only rarely gets used. But once multiple systems begin to whisper the same basic message, the interpretation changes. We are still not allowed to say the tunnel is broad, but we are no longer allowed to pretend it barely exists. The confidence shifts from, "This almost never happens," to, "This happens enough that our story has to keep accounting for it in a serious way." That is a substantial change in scientific mood. And mood, in the healthy sense, matters. It determines whether a field treats new discoveries as incidental or as clues. It shapes what questions younger researchers decide are worth their time. It changes which simulations get run, which parameter spaces get widened, which surveys are considered strategically important. A discovery does not need to overturn all prior knowledge to alter the intellectual weather. It just needs to make old certainty feel expensive to maintain. TOI-6894b may be one of those discoveries. Not alone, perhaps. Science rarely moves on one object alone. It moves on clusters of evidence, on accumulating discomfort, on the gradual convergence of theory and observation under pressure. But some systems become memorable because they crystallize the pressure clearly enough that even outsiders can feel it. This is one of them. The star is small enough, the planet is large enough, the mismatch is plain enough, the theoretical tension is real enough. The wider galactic implication is serious enough. Everything needed for the case to linger is already there. And that lingering matters because it alters the way we see the common sky. The night sky, even when stripped of romance, has a tendency to feel sordid. Stars look like points, categories look stable. The deeper one goes into astronomy, the more those points turn into neighborhoods, histories, chemical records, dynamical systems, failed expectations. What once seemed like a clean field of lights becomes a place crowded with violated assumptions. A quiet red dwarf is no longer just a point. It becomes a possible site of architectural surprise. A dim star is no longer necessarily a modest one in outcome. That is a subtle transformation, but it has real force. It means the universe becomes not only larger, but less complacent. Not chaotic, not theatrical, less complacent. The ordinary does not stay ordinary under inspection. The common does not stay simple. The background does not stay background. And perhaps that is one of the deepest patterns in science. Every time we think we have identified the merely average setting, the place where fewer revelations ought to remain, reality quietly reminds us that average is one of the most misleading words we have. Average does not mean exhausted. It does not mean transparent. It does not mean fully understood. Around the most common stars in the galaxy, there may still be worlds waiting that continue this same patient humiliation of our confidence. And that humiliation, when it is honest, is not bleak at all. It is one of the ways knowledge stays alive. If everything fit too easily, the universe would become smaller every time we learn more about it. That is not what has happened. Again and again, understanding has made the world less magical in one shallow sense, and more astonishing in a deeper one. We lose the comforting illusion that our first picture was close to complete, and in exchange, we gain a reality that is more intricate, more exacting, and strangely more intimate. A star stops being a point of light and becomes a system with a biography. A planet stops being an abstract detection and becomes a specific challenge to our expectations. The cosmos becomes less decorative and more real. TOI-6894b lives inside that more real universe. It is worth noticing how unceremoniously such changes begin. No great cosmic trumpet announced this planet, no visible spectacle unfolded in the sky. A survey telescope watched a field of stars, One of those stars dimmed by a small amount at regular intervals. A possible explanation emerged. Follow-up work narrowed the possibilities. A world took form inside the measurements. Then, only after the object was secure enough to discuss seriously, the larger implication began to spread outward. This is what discovery often feels like from the inside. Not a lightning bolt, a tightening. That tightening is almost the opposite of how popular imagination pictures science. People like the moment of revelation. They like the clean before and after. They like the idea that one new fact suddenly flips the whole table. But many of the most consequential findings do not behave that way. They work more slowly. They keep the old theory largely intact, while making one piece of its emotional scaffolding untenable. Then the field has to live with the discomfort long enough to make itself more precise. This planet is exactly that kind of discomfort. Because if we strip the story back to its bones, the problem remains elegantly simple. A very low-mass star should, on average, come with a relatively low-mass protoplanetary disk. A relatively low-mass disk makes it harder to build a giant planet quickly enough to gather a large gas envelope before the gas disperses. Yet there is a giant planet there. The discovery does not merely add complexity. It insists that our sense of what harder means needs to stay open to surprise. And harder is not the same thing as rare in any everyday, dismissive sense. That word can mislead us. Something can be difficult to produce under typical conditions, and still occur often enough across the galaxy to matter profoundly. The Milky Way is the kind of stage on which low-probability events can become entire hidden populations. A slight underestimation in formation efficiency around red dwarfs could scale into a vast correction once multiplied by the number of such stars. That is why the discovery feels statistical as much as physical. One world is not just one world here. It is a probe inserted into a much larger demographic question. How many giant planets are actually out there around stars we once treated as unlikely hosts? How much of apparent scarcity is genuine scarcity, and how much is the residue of incomplete detection, biased sampling, or overconfident modeling? Those are not ornamental questions. They touch the real shape of the galaxy. And the shape of the galaxy matters, because humans are always tempted to mistake their local version of reality for the cosmic one. Our own solar system is a powerful source of that temptation. It feels balanced. It feels legible. It gives us a clean hierarchy. Rocky worlds near the star, gas giants farther out, long periods, broad spacing, a kind of measured dignity in the arrangement. Even after decades of exoplanet discoveries have loosened our attachment to that template, some part of the mind keeps wanting the universe to remain proportionate in familiar ways. Then something like TOI-6894b appears and reminds us that proportion is one of the first comforts to go. A small star can host a planet that feels out of scale with it. A close orbit can belong to a history we do not yet fully understand. A common stellar class can contain planetary arrangements that still make theorists uneasy. Once those things are true, the old emotional order does not survive unchanged. The cosmos stops feeling like a place where every level of size and consequence politely matches. And perhaps that is exactly why the discovery is so satisfying to stay with. It is not merely weird, it is clarifying. It exposes a broader habit of mind. We prefer a universe where visible modesty implies hidden modesty. We expect a faint star to lead a modest planetary life. That expectation is not silly, but it is vulnerable. The moment it fails, we are forced to admit how often we have used brightness and scale as substitutes for understanding. The galaxy has no reason to honor that shortcut. There is another layer here, and it concerns time. Red dwarfs are not only numerous, they are long-lived on scales that can be hard to feel without flattening them into useless numbers. A star like the Sun burns brightly, but on cosmic terms is spending itself at a faster rate than a much smaller red dwarf. Many red dwarfs will persist for staggeringly long spans, quietly converting hydrogen while brighter, larger stars live and die on shorter schedules. That longevity gives them a kind of galactic patience. They are not flashy, they are enduring. So when one of these quiet, durable stars turns out to host a giant planet that strains our formation expectations, the result acquires a deeper kind of irony. The most long-burning, numerous stars in the galaxy may still be among the least emotionally understood in the planetary sense. We know they are there. We know they dominate the census. We know they matter for exoplanet searches and long-term galactic habitability discussions. Yet a discovery like this suggests that their possible system architectures may still contain more hidden variety than our calmer summaries let on. That is a humbling combination: dominance without vividness, abundance without intuitive familiarity, importance without theatrical presence. Human beings miss things arranged like that all the time. We miss the background system because it does not announce itself as crisis or spectacle. We normalize the infrastructure because it is always there. Only when the infrastructure behaves unexpectedly do we realize how little we had actually felt it. Red dwarfs have some of that quality in astronomy. They are the background population. A discovery like TOI-6894b is what happens when the background suddenly acquires enough detail to push back. And it pushes back in a particularly elegant way because it does not deny the old logic outright. It narrows it, it conditions it, it turns certainty into tendency. That is one of the most refined forms of correction science can offer. The older account survives, but with less swagger. Giant planets around very low-mass stars remain difficult to form under standard expectations. They remain uncommon compared with other outcomes. Yet difficult is no longer allowed to drift so close to surely absent that everyone forgets the difference. This is why wording matters so much in frontier science. A careless phrase can quietly overstate the confidence of a model. Then a discovery arrives, and the phrase becomes embarrassing. Should not exist is useful as a title because it carries the emotional truth of the surprise. But the sober truth beneath it is better and more durable. Under the most comfortable reading of current theory, such a planet is deeply unexpected, and that unexpectedness is now part of the evidence. That distinction is not a limitation. It is what keeps the wonder clean. Because clean wonder does not need exaggeration. The facts are already doing enough. A red dwarf with about a fifth of the sun's mass, a giant planet crossing its face every few days, a world roughly Saturn-sized, a system discovered through the patient watching of light, a planetary arrangement that puts real pressure on how we think small stars spend their formation budgets. That is already more than enough to live with for a while. The longer you do live with it, the stranger one feature becomes. Not the planet's size by itself, not the star's faintness by itself. The pairing. That is the enduring image. The smallness of the host and the largeness of the companion remain in tension no matter how many careful explanations we wrap around them. And that is useful because it keeps the theory tethered to something memorable. Even as the field grows more technical in its response, the mind can return to the same physical intuition. This looks like too much planet for that star. Sometimes a whole scientific question can be carried in one image like that. A village workshop, somehow, launching an ocean liner. Not because the analogy is exact, it isn't. No analogy ever is. But because it preserves the feeling of material mismatch without lying about the underlying issue. The challenge is not one of taste. It is one of resources, timing, and process. There does not seem to be enough in the starting environment to make the final outcome comfortable. And discomfort is a powerful engine of progress when it remains specific. It prevents the field from congratulating itself too early. It keeps observation valuable. It protects the possibility that the commonest stars in the sky may still be hiding outcomes that make our neatest planetary stories feel provincial. That is a quiet kind of revelation, but a deep one. Once it takes hold, the night does not feel emptier. It feels less finished. Less finished is exactly the right feeling, because a discovery like this does not simply add one more item to an already complete picture. It puts a seam back where we had started painting over one. That seam runs through some of the most ordinary-looking stars in the galaxy, which is what makes it so difficult to ignore once you have seen it. The spectacular corners of the universe were always allowed to be strange. It is far more destabilizing when the common background starts refusing simplicity. There is something almost unfair about the way the sky does this to us. We spend years refining categories, improving surveys, calibrating models, and building a more disciplined sense of what tends to happen. Then the correction arrives, not as a contradiction of everything, but as a measured exception in exactly the place where our confidence had begun to sound smoothest. It is not the grand collapse of knowledge. It is the erosion of complacency. And that kind of erosion can run a long way. Take the phrase low-mass star. In specialist language, it is precise enough. In the imagination, though, It does more than specify a physical class. It drags along an entire atmosphere of expectation. Lower mass suggests reduced scale, reduced budget, reduced consequence. A smaller star feels like a smaller story. Yet in the galaxy, small stars are not a side note. They are the dominant population. Their collective importance overwhelms their individual modesty. That is one of the strangest inversions in astronomy. The things most likely to be underestimated by intuition are often the things most likely to define the whole. TOI-6894b pushes directly into that inversion. It forces us to hold two facts together that do not sit comfortably in the same sentence until we make ourselves stay with them. The host star is small, around a fifth the Sun's mass. The planet is a giant world, broad enough in size to belong to a category many people instinctively reserve for systems with more generous beginnings. Those facts coexist whether or not our narrative is ready for them. And readiness is part of the issue. Science is not only a machine for producing facts, it is also a culture of prepared attention. It decides what counts as routine, what counts as noise, what counts as a candidate worth chasing, what counts as an anomaly worth reorganizing thought around. A field can miss the full meaning of its own discoveries for a while simply because it does not yet have the right emotional posture toward them. The measurements may be there before the significance settles in. That is why repeated cases matter so much. One world can be tolerated as an astrophysical eccentric. 2 or 3 begin to alter posture. The category, possible but negligible, starts to weaken. Researchers do not need to panic or proclaim a revolution. They only need to become less comfortable with the old emphasis. The adjustment begins there, in tone, before doctrine. This is not the kind of thing most people are trained to notice when science is described publicly. We tend to hear about ideas as if they come in neat boxes, labeled correct and incorrect. But real inquiry often moves through gradients of confidence. A theory can remain broadly successful, while a specific confidence inside it becomes less tenable. A rule of thumb can stay useful while losing the right to sound almost absolute. A model can still be the best available account while also becoming visibly incomplete in a particular regime. Low-mass stars and giant planets may be one of those regimes. The deeper reason that matters is not technical elegance. It is reality density. The galaxy is dense with systems we cannot know well by casual analogy. Every time we let a shorthand phrase stand in for a whole domain of outcomes, we risk flattening something that is still in motion. A red dwarf is not just a small version of the Sun. A giant planet around one is not just a weird Jupiter. A short-period orbit around a dim host is not just a familiar hot Jupiter story transplanted to a smaller stage. Each shortcut removes some of the actual texture. The discovery hurts, in the best sense, because it makes the shortcuts expensive. And expense changes behavior. It changes which comparisons we trust. It changes how carefully we speak. It changes how future detections will be greeted. After a discovery like this, another giant planet around a tiny star is no longer processed as pure novelty. It lands in a more prepared landscape. The first case cracks the shell. The next cases enter through the crack. Eventually, the shell itself is remembered as an artifact of an earlier, less patient understanding. That is how categories evolve, quietly, accumulatively, often without the public noticing, until the new picture already feels normal. There is a beautiful irony in that process, because the very stars that encourage long-duration thinking are the ones involved here. Red dwarfs live for extraordinary lengths of time. They burn slowly. They do not rush. If any part of the galaxy teaches patience by example, it is this one. And now patience is exactly what the science demands from us. Not excitement alone, not headline astonishment. Patience with uncertainty. Patience with incomplete census data. Patience with the possibility that the commonest stars may force one of the next refinements in planetary theory. Patience is hard because the mind wants an immediate story. Was the disk unusually massive? Did the planet form far from the star and spiral inward? Did solids collect more efficiently than expected? Did some less common pathway, perhaps one that only matters under a narrow set of conditions, open up long enough to create a giant planet where the ordinary route would struggle? Those are all good questions, but they are not the same as an answer. And one of the healthiest things we can do with a discovery like this is resist the urge to collapse a menu of possibilities into a single favorite narrative just because our psychology prefers closure. Closure is attractive for another reason too. Once a strange object is successfully explained, we can put it back into the cabinet. It no longer follows us around. It no longer changes the atmosphere of the category. It becomes one more solved case. But TOI-6894b is not there yet, not in the deeper sense. The planet is securely present. Its formation history is not. That gap between what is known and what is not known is not a flaw in the story. It is the story's living center. And it becomes even more compelling when you realize how much of astronomy depends on this kind of reverse engineering. We almost never get to watch the crucial stages unfold. By the time we detect a mature exoplanet, the formative disk is gone. The primordial materials have either become planets, been blown away, fallen inward, been scattered out, or otherwise ceased to exist in the arrangement that mattered during construction. We are like archaeologists, arriving long after the city has become ruins, except the city is still standing and the blueprints are what vanished. So we infer from survivors. We read present structure as evidence of prior conditions. A giant planet around a tiny star is therefore not just an object, it is a fossil of a process we did not witness. It is the surviving monument of some successful chain of events, in an environment where success of that kind was supposed to be especially hard. That makes the planet feel less like an ornament and more like a testimony. A testimony to what, exactly, is still unsettled. Maybe it is testimony that our sense of disk mass versus host mass needs more flexibility at the low end. Maybe it is testimony that the efficiency of core growth in some red dwarf systems has been underestimated. Maybe it is testimony that migration histories are doing more of the explanatory heavy lifting than we used to think. Maybe it is testimony that the rare tale of giant planet formation around low-mass stars matters more than expected because the stars themselves are so numerous. Each possibility changes the galaxy in a slightly different way. That last possibility is especially important. Even if systems like TOI-6894 remain uncommon, their absolute number could still be very large, simply because red dwarfs are so abundant. It is one thing to call something rare in a room of 100 people. It is another to call something rare in a city of hundreds of billions. The arithmetic does not merely scale up the count, it changes the emotional meaning of rarity itself. Astronomy is full of these emotional misfires. We hear low probability and picture negligible presence. We hear small star and picture small consequence. We hear exception and picture decorative irrelevance. But large populations do not obey our emotional bookkeeping. A rare pathway used by a dominant stellar class can still populate the galaxy with more worlds than we know how to picture honestly. Which means that what feels marginal at the level of theory can become substantial at the level of the Milky Way. This is one of the reasons the discovery keeps widening instead of shrinking the longer we stay with it. At first, the surprise is local. That star, that planet, that mismatch. Then it becomes procedural. How did it form? Then statistical. How often does this happen? Then galactic. What have we been assuming about the majority of stars? And finally, it becomes philosophical in a quiet way. How often do our categories become smoother than reality, simply because they have worked well enough for a while? Once you ask that last question, the planet is no longer just a curiosity in a catalog. It becomes a reminder that the cosmos does not have to violate physical law to violate mental habit. A single well-measured world can be enough to do that. And the mental habit at stake here is powerful. We tend to believe that modest-looking settings produce modest outcomes. We trust apparent scale more than hidden process. We underestimate what can happen in the quiet districts of reality. Yet the universe keeps putting leverage in places our intuition would never think to search. A dim star, a giant companion, a few photons lost during transit, and suddenly, one of the most common stellar populations in existence begins to look a little less settled than it did before. That is not a loud revelation. It is a durable one, and those are often the ones that last. They last because they do not depend on novelty alone. Novelty burns off quickly. Once the first surprise fades, only structure remains. And the structure here is unusually strong. A giant planet around one of the smallest known stars to host a transiting giant planet is not merely a curious pairing, it is a pressure point. It sits exactly where a lot of quiet assumptions intersect. Disk mass, formation efficiency, migration, detection bias, population statistics, and the tendency of common stellar categories to become emotionally oversimplified. That last point may be the easiest to miss because it sounds softer than the rest, but it may be the one that reaches furthest. Human beings often mistake familiarity of label for familiarity of reality. We say red dwarf and feel as though we have already reduced the object to something manageable. The phrase seems to shrink the star before we have really thought about what that category contains. Small, cool, numerous, long-lived. Good targets for exoplanet searches. Then the mind moves on. But categories are only useful until they start numbing us to internal variety. TOI-6894b breaks that numbness. It tells us that one red dwarf cannot simply stand in for all the others when it comes to planetary outcomes. That sounds obvious in a trivial sense. Of course, no one star stands for all stars, but psychologically we do it anyway. We let broad trends congeal into background expectation. We begin to feel that certain kinds of systems belong in certain neighborhoods of the galaxy and not in others. Then the measurements arrive, and the feeling has to retreat. There is an old temptation in astronomy to arrange the cosmos as though it were a series of clean districts. Massive stars with one family of stories, sun-like stars with another, low-mass stars with another still. That sorting impulse is understandable. It helps us think. Yet the universe keeps resisting any version of the map that becomes too elegant. The districts bleed into one another. Probabilities overlap. Edge cases recur. A category that looked modest turns out to contain a few examples that are not modest at all. And once you admit that, the atmosphere of the Milky Way changes slightly, not in appearance, in meaning. The stars still look like points. The catalog entries still look clinical. The transit depths and mass estimates still arrive in tables and plots rather than in thunder. But behind that quietness, a larger thought begins to gather. Perhaps the galaxy's dominant stellar population has been hosting a wider set of planetary architectures than we gave it credit for. Perhaps the reason the old simplification felt so stable was not because it was final, but because it was easy to repeat. Easy repetition is one of the most dangerous things in knowledge. A sentence can become familiar long before it becomes complete. Around small stars, giant planets should be scarce. That is a good sentence. It remains broadly useful. But the moment it becomes emotionally translated into around small stars, giant planets basically do not happen. It begins to accumulate a false smoothness. That false smoothness is what discoveries like TOI-6894b abrade. Science needs abrasion. Without it, models harden into manners of speech rather than instruments of inquiry. And there is something wonderfully severe about the way the abrasion happens here, not by rhetoric, by light. A tiny dimming, repeated on schedule, saying the same thing over and over. Whatever story we preferred, this world is already in orbit. It has already crossed the star. It has already left its mark in the data. The argument begins from that stubborn fact and only then turns toward theory. That order matters. It means the cosmos gets to speak first. We often forget how asymmetric this relationship is. Human beings do not negotiate with the sky. We do not tell a system what would be most conceptually convenient. We construct expectations, and then the universe either tolerates them or declines to. A discovery like this is the universe declining, not angrily, not dramatically, just by existing in a place where our expectation had begun to feel too secure. And because the host star is so small, the decline feels personal to the theory. If the planet orbited a somewhat larger star, the discomfort would be milder. There would be more room to shrug, more room to say this falls within the broad, messy middle of formation outcomes. But TOI-6894 sits close to the lower stellar mass territory, where those shrugs lose their ease. The host star is doing essential work in the story. It is not backdrop, it is the hinge. This is why, around that star, matters more than planet that shouldn't exist by itself. The same planet elsewhere would carry a different intellectual charge. Here, the host converts the planet from a mere object into an argument about thresholds, budgets, and the dangers of turning tendency into boundary. The star does not just illuminate the planet, it defines the problem. And from there, the story widens again, because once we begin talking about thresholds, we are really talking about how science handles edge conditions. Every field has them. places where the broad rule starts to thin out, where an average ceases to feel like a safe guide, where the tails of the distribution stop being decorative. Edge conditions are where systems reveal whether our understanding is robust or only comfortable. They are where the map is forced to admit how much it had been smoothing over. Low-mass stars hosting giant planets may be one of those edge regions for planet formation theory. Not a place where the theory fails wholesale, but a place where its simplifications begin to show their seams. That is a fruitful place to be. It means more than one future is still possible. Maybe ongoing surveys will show that such planets remain genuinely rare, and that TOI-6894b belongs to a thin tail of unusual histories. If so, the lesson will still matter, because tails tell us what a system permits at its extremes. Or perhaps additional detections will reveal that giant planets around very low-mass stars are not common exactly, but common enough to demand more substantial changes in our population models and formation assumptions. That would matter even more. In either case, the discovery has already won its place. It has made certainty more expensive. And cost is what often separates live science from dead language. When a phrase becomes too cheap, we repeat it without feeling its burden. Small stars do not easily make giant planets. Fine. Useful. But now that sentence must carry a visible weight behind it. It must remember TOI-6894b. It must say what it means with more discipline. It must leave room for the giant world that is already there. Crossing a tiny red star every few days, and forcing precision on everyone who speaks about such systems afterward. There is something almost ethical in that kind of correction. Not moralistic, just clean. The world insists on being described with the right amount of humility. Humility in this context does not mean vagueness. It means saying exactly what is strong and exactly what is unsettled. The detection is strong. The planet is real. The host star is exceptionally small for a transiting giant planet system. The formation pathway remains uncertain. Giant planets around such stars are still understood as difficult to produce under standard expectations. Their true population around red dwarfs is still something surveys are helping reveal. That is not a weaker story than the sensational version. It is a stronger one because it can survive the novelty cycle. And survival matters. Most scientific headlines vanish because they depend too much on the first jolt of surprise. This one can last because the surprise is structural. It is attached to the way we think about the most common stars in the galaxy. It is attached to the possibility that the calmest-looking category may still be hiding unresolved complexity. It is attached to a broader human habit of underestimating what quiet systems can do. That habit reaches far beyond astronomy, which may be why this discovery resonates even with people who do not memorize exoplanet catalogs. We all know what it is like to assume that modest appearance implies modest capacity, or that the background is simpler than the foreground, or that common things are fully understood because they are common. Time and again, reality punishes those assumptions. The galaxy is simply doing it on a larger stage. A tiny red star with an oversized companion is one expression of that larger truth. Not a metaphor first, a real system first. The metaphor comes later because human beings need some way to carry the shock of proportion in the mind. A small-town airport quietly handling intercontinental jets. A short receipt ending in an impossible total. A little lamp with a parade float moving around it in the dark. Those images stay with us because the system itself stays with us. Even after the technical details settle, the pairing remains. Too much planet, our instincts say, for that star. And the longer the planet continues to exist in the data, the more clearly we are forced to admit that the too much was never a fact about the universe. It was a fact about where our expectation had quietly stopped evolving. And that is a difficult thing to admit, because expectation does not feel like imagination when it has been reinforced by years of good work. It feels earned. In many cases, it is earned. That is what makes these discoveries so instructive. They do not arrive to correct fantasy. They arrive to correct confidence that had reason behind it. The correction is therefore not humiliating in a cheap way. It is the useful humiliation of being made more exact. Exactness matters especially in a field like exoplanets, where the temptation to flatten every object into a generic marble is so strong. There are now so many worlds known beyond the solar system that wonder itself has to become disciplined, or it turns into fog. Every new detection cannot simply be another astonishing planet. The mind stops listening. The only discoveries that really endure are the ones that alter the shape of understanding. TOI-6894b does that because it sits at the junction of several things that matter at once: host star mass, disk expectations, giant planet occurrence, and the broader question of what the Milky Way is mostly like when we stop projecting the sun's neighborhood onto it. That last point may be the most quietly radical of all. We still carry, often without noticing, a solar system-shaped emotional model of the galaxy. Even after learning that exoplanets can be wildly different from our own arrangement, many people still imagine the broader stellar population through a sun-filtered lens. Stars feel sun-like unless reminded otherwise. Planetary systems feel loosely familiar unless evidence becomes too vivid to ignore. But the Milky Way is not organized around what is vivid to us. It is organized around what exists in overwhelming numbers. And what exists in overwhelming numbers are stars smaller, dimmer, and calmer than the one that governs our days. So if those stars can build giant planets through channels we underestimated, then the ordinary galaxy becomes a less settled idea than before. Not a stranger galaxy in the theatrical sense, a stranger galaxy in the demographic sense, which is often more consequential. It means the background population may carry more unexpected architecture than our inherited intuition allowed. It means the ordinary may be less homogeneous than we thought. It means the default settings of the Milky Way may still be under active revision. There is something deeply satisfying about that, because it preserves mystery in the right place. Not mystery as vagueness, not mystery as ignorance, mystery as the honest recognition that an object can be well measured and still not fully understood. The world is there. The orbit is there. The host star is there. The theoretical discomfort is there. What remains open is the causal chain that made this pairing possible, and the population question of how often similar chains succeed elsewhere. That kind of mystery has traction. It moves research forward. It also has a way of changing how we look at data itself. A transit curve can seem dry to someone outside the field, just a tiny fluctuation in brightness over time. But once you understand what is at stake, the curve acquires drama without needing any embellishment. That dip in light is not just a signal, it is a world cutting across a star that our simpler expectations had mentally reserved for more modest outcomes. A small graph suddenly becomes the visible scar of a broken assumption. And perhaps that is why modern astronomy can feel so intimate when it is working at its best. The distances are absurd, but the evidentiary form is often small, tiny shifts, slight dimmings, marginal wobbles, subtle spectra. We learn immense things from delicate traces. We revise whole categories because of very little light. There is a tenderness in that method, a humility built into the scale of the evidence itself. Nothing here is forced. The universe gives us a slight change in brightness. And if we are careful enough, patient enough, and honest enough, that slight change can tell us that one of our assumptions about the commonest stars in the galaxy is no longer as safe as it used to be. Patience really is the right word. Red dwarfs themselves almost seem to insist on it. They burn slowly. They persist. They do not flood the cosmos with flamboyant urgency. They are stars of long duration, and perhaps it is fitting that our understanding of them should also require duration. Not one discovery, one headline, one model update, and done. A longer adjustment. A slower widening of what counts as plausible. A more cautious language around giant planets and low-mass systems. A more serious interest in how often these systems occur and what histories might create them. The beautiful thing about patient corrections is that they often reach further than dramatic ones. A dramatic claim can be exciting and then evaporate. A patient correction changes the grammar of a field. It alters how people ask questions, what they count as surprising, which data they scrutinize harder, what they permit themselves to infer. It changes the weather without ever becoming a storm. TOI-6894b feels like that kind of event. Not because it destroys the old framework, but because it may permanently lower our confidence in one of its smoother simplifications. And simplification, that is the scientific version of maturity. Not accumulating more facts alone, but becoming less careless with the ones you already have. There is a broader human resonance here too, one that has nothing to do with sentimentality and everything to do with pattern recognition. Again and again, the world turns out to be more varied in its quiet zones than our psychology predicts. We underestimate backgrounds. We neglect the ordinary. We assume the common thing is fully mapped because it is common. Yet common things often contain the most hidden variety precisely because they are so widespread. Small differences repeated over huge populations create outcomes our intuition is too parochial to anticipate. That is true in nature. It is true in history. It is true in social systems. And it appears to be true in planetary systems as well. A red dwarf with a giant planet is not just an exoplanet story then. It is also another instance of a deeper reality. The ordinary category is often where our errors grow largest, because that is where we stop paying close emotional attention. We reserve our awe for the rare giant, the supernova, the black hole, the collision. Meanwhile, the galaxy's most numerous stars go on being quietly misimagined, until one of them refuses. It refuses by having a world too large for our comfort. It refuses by dimming at the wrong time, in the wrong way, according to the smoother version of our expectations. It refuses by forcing us to distinguish between improbable and absent, between trend and law, between what standard models strongly favor and what the universe still manages to produce in spite of that favoring. This is not a small clarification. It is one of the major disciplines science keeps having to relearn. The discipline is simple to state and hard to live by. Never let the usefulness of a pattern tempt you into forgetting the reality of its tales. That may be one of the cleanest ways to understand what is happening here. Planet formation models had real success. They still do. But a successful pattern is not permission to become emotionally absolute. The tails of the distribution matter. Rare pathways matter. Outlying conditions matter. Selection effects matter. In a galaxy this large, anything physically allowed and not vanishingly suppressed begins to acquire demographic seriousness. So when a giant planet turns up around a star this small, it is not merely an oddity to be admired. It is a reminder that the tails are part of the universe too. And because the host stars involved are so common, those tails may reach farther into the Milky Way than our old wording let us feel. That is where the story starts to become almost tender, not soft. Tender in the sense of careful, exposed, a little raw. We are watching a field become more accurate in real time. We are watching one of the galaxy's most familiar stellar populations grow slightly less emotionally familiar. We are watching the cosmos keep one of its oldest promises, that knowledge, if it is real knowledge, will not merely make the world clearer, it will make it less smug. A faint red star, then, is no longer just part of the background. Somewhere in the dark, one of them is carrying a giant world around itself every few days, and the existence of that world means our picture of what belongs around such stars has already begun to loosen. Once you feel that properly, the night changes again, not into chaos, into a place where the common things have not finished revealing what they are. And that may be the most durable effect of all. Not that one planet surprised astronomers, but that an entire class of stars becomes harder to take for granted afterward. Taking things for granted is one of the mind's oldest economies. It is how we survive everyday life. We stop freshly interrogating the floor, the weather, the wiring in the walls, the social rules of a city. In science, some version of that economy is necessary too. Researchers cannot rebuild first principles every morning. They need working expectations, stable baselines, trusted correlations. But the price of those economies is always the same. Eventually, some corner of reality becomes more familiar in language than in fact. And when the correction comes, it tends to come from precisely the place we had started to treat as settled. For exoplanet science, red dwarfs may be one of those places. Not because they were neglected. In one sense, the opposite is true. They have been central to some of the most exciting searches for terrestrial worlds beyond the solar system. Their small size makes some planetary signals easier to detect. Their abundance makes them unavoidable. Their long lifetimes make them cosmically consequential. They are not obscure stars, but there is a difference between being studied and being emotionally well imagined. A class of objects can be scientifically important and still mentally reduced. It can become a kind of shorthand, a reliable box in which expected behaviors are stored. The box is what discoveries like TOI-6894b damage. Once the box is damaged, a more interesting picture begins to emerge. Red dwarfs stop feeling like stars with one dominant planetary character, and start feeling like stars whose apparent modesty hides a broader range of possible histories. Some may host small rocky worlds in compact systems. Some may host no planets we can yet detect. Some, it now seems, can host giant planets that make our old formation story feel a little too neat. The category becomes not vague, but plural. Plurality is often the true shape of understanding. The world becomes more specific and less monolithic at the same time. That is why a discovery like this has a strange calming effect if you stay with it long enough. At first it is a disturbance. It sounds like disorder, a planet where it should not be, a giant world around an undersized star. But as the initial jolt fades, something better replaces it. You begin to feel not chaos, but range, not violation, but loosened overconfidence. The universe is not becoming less intelligible, it is becoming less overcompressed. This is one of the deepest ways science changes perception. It does not always give you a single new image. Sometimes it removes a false economy from the old image and lets more of reality back in. Small stars are no longer mentally compressed into small outcomes. That is already a perceptual shift, and a significant one. It reaches further than planets, because once you have seen that shift in one place, you start noticing the habit everywhere. We are constantly underestimating quiet categories. The unshowy category, the background class, the familiar setting, these are the places where simplification accumulates most aggressively. We save our vigilance for the dramatic edge case, then discover that the background was carrying hidden diversity the whole time. Exoplanets around red dwarfs are one version of that story. Biology, geology, history, and social systems all have their own versions too. The ordinary is often only ordinary at low resolution. TOI-6894b is a high-resolution correction, and it is especially powerful because the correction is so materially grounded. We are not dealing with a philosophical suggestion floating free of evidence. We are dealing with a measured planetary system. A host star about 1/5 the mass of the Sun, a giant planet with a radius roughly comparable to Saturn's, a tight orbit of just over 3 days, a transit signal that turned a small dip in starlight into a problem for our confidence. The concreteness of the object keeps the meaning from becoming vague. The thought has weight because the world has weight. There is a kind of honesty in that. It reminds us that astronomy is at its best when its largest conceptual revisions begin with stubborn, physical particulars, not with slogans, not with inflated metaphors, a specific star, a specific orbit, a specific mismatch. Then everything else grows from there. And everything does grow from there, because the discovery keeps opening onto broader questions. How much scatter is there, really, in the relationship between stellar mass and the kinds of planets that ultimately form? How often do low-mass stars start with disks rich enough, or structured enough, to permit rapid core growth and large gas capture? How often do migration histories move giant planets into the short orbits where we can detect them more readily? How much of our current view is a portrait of nature, and how much is still a portrait of our instruments? These are not decorative follow-ups. They are the future shape of the subject. That future shape may end up being less dramatic than the headlines, and more consequential than they are capable of expressing. Science often works like that. The public hears "planet that shouldn't exist" and imagines a scandal. The field hears "planet around a very low-mass host" that strains standard formation expectations, and begins quietly rethinking parameter space, survey priorities, statistical interpretation, and the range of models it is willing to treat as serious. The headline is louder, the field's response is deeper, and depth is what gives a discovery afterlife. There is another reason this system lingers, and it has to do with proportion at the level of feeling. Human beings do not just reason with categories, we reason with balance. We expect a kind of visual and causal symmetry from the world. Small source, small result. Large source, large result. Modest environment, modest architecture. A planet like TOI-6894b injures that symmetry. It produces a tiny but real wound in our intuitive bookkeeping. We look at the star and think, that should not be enough. Then we look at the measurements and realize enough for what was the wrong question all along. Because enough in the universe is rarely a simple quantity. It is a function of process, sequence, timing, local concentration, migration, and chance within constraint. An apparently meager beginning may be enough if the pathway is efficient. A generally unlikely route may still succeed if several favorable conditions align. A category that tends toward one outcome may still harbor another in its long tail. That is how complex systems behave. They do not mock the average. They just refuse to worship it. The phrase "should not exist," then, becomes more revealing the longer we sit with it. At first it sounds like a statement about the planet. By the end it sounds more like a statement about a style of thinking. It names the point where a useful expectation had begun to overextend itself. It names the place where a probability gradient had started masquerading as a boundary. It names a sentence that worked so well in simplified form that we forgot how conditional it had always been. That is the kind of forgetting astronomy cures, repeatedly. And there is a certain gratitude built into that cure, even when the feeling arrives through discomfort. We get to live in a universe that continues resisting our premature neatness. We get to inhabit the moment when a field becomes more exact. We get to watch the night sky lose one more layer of false simplicity. That is not a failure of understanding. It is understanding happening properly. The planet itself, of course, is indifferent to all of this. It does not exist to educate us. It is simply following its orbit, crossing its little red star, leaving its periodic signature in the light, as it has done whether anyone was watching or not. There is something deeply grounding in that indifference. The meaning is ours. The existence is its own. Maybe that is why the discovery feels so calm beneath its surprise. It is not theatrical. It is just firm. The world is there. The older comfort is less secure. The most common stars in the galaxy are still not finished teaching us what planetary systems can be. No one needs to shout. If anything, the right response is quieter, to let the implications settle, to feel how much of the Milky Way is made of stars like this, dim and numerous and long-burning, to recognize that even uncommon outcomes around such stars could amount to enormous numbers of actual worlds, to understand that what looks statistically marginal at the scale of a model can become cosmically substantial at the scale of a galaxy, and to realize, finally, that the phrase "ordinary star" may have been doing far less explanatory work than we thought. Because ordinary is not the same as exhausted. Ordinary is not the same as simple. Ordinary is not the same as fully seen. A category can dominate reality and still remain partially hidden from intuition. In fact, that may be one of the places where intuition fails most reliably. A tiny red dwarf with a giant planet is not merely a strange pairing then. It is a reminder that the quiet majority of the cosmos may still be carrying outcomes that exceed the confidence of our cleaner stories. Once you feel that, the dark between the brighter stars stops feeling empty in quite the same way. It becomes populated not just by objects, but by possibilities that our language has not yet fully learned how to hold. And that inability of language to fully hold reality may be one of the most important feelings this story leaves behind before it ends. Not because language is useless, but because words like common, small, rare, likely, giant, and ordinary all begin to loosen under pressure if we treat them as more than temporary handles. They remain useful. They just stop being safe places to rest, too completely. Around a star like TOI-6894, every one of those words has to be carried with a little more care than before. That is often what progress feels like at close range. Not the arrival of a perfect replacement picture, but the removal of an old ease. The field does not become speechless. It becomes more disciplined in what it lets itself say casually. A giant planet around a very low-mass red dwarf is no longer just the sort of thing theory disfavored in an abstract way. It is now part of the observed world, part of the burden every future statement about such systems has to bear. There is something deeply healthy about that burden. It keeps astronomy from becoming a literature of elegant approximations that forget to answer to the sky. The sky is always untidier than the sentence that temporarily describes it. We know that, but every so often an object arrives that makes us feel it again, not as a slogan, but as a physical discomfort in thought. This planet is one of those objects. If we pull back far enough, the whole episode begins to look like a lesson in scale and humility, disguised as a discovery story. The surface fact is local, one giant planet around one small red dwarf. The deeper truth is wider. When our models are built around what usually happens, they can still leave us emotionally underprepared for what the tales of reality permit. And when those tales belong to the most numerous stars in the Milky Way, the gap between emotional expectation and cosmic actuality can become enormous. That is the galactic version of the mismatch. Not merely a large planet around a small star, but a potentially meaningful population hiding inside what we once treated as an unlikely corner of formation theory. A low probability attached to a vast denominator becomes a lot of worlds. That arithmetic keeps returning because it never really stops mattering. Human intuition has no native respect for sample sizes this large. We hear uncommon and imagine negligible. The Milky Way hears uncommon and, very often, still produces an empire of examples. So even if systems like TOI-6894b remain rare by the standards of red dwarfs as a whole, their existence still changes the atmosphere of the galaxy. It means there are likely many such worlds, not just one. Not this one discovery as a singular cosmic joke, but a class of outcomes that reality appears willing to permit, perhaps grudgingly, perhaps only under special conditions, but permit them it does. And permission is everything here. Because once nature permits a configuration, the scientific question changes from, could this happen at all, to how often, by what route, and with what consequences for the rest of the system. That is a much richer set of questions. It opens the possibility that giant planets around low-mass stars may sometimes alter orbital histories of other planets, reshape the distribution of smaller bodies, or create final architectures that we would never have predicted from the star alone. It suggests that the quiet neighborhoods of the galaxy may host more complicated internal politics than their facades imply. That idea has emotional force because it mirrors something we know from ordinary life. The outside of a system often tells you less than you think. A calm institution can hide deep turbulence in its past. A modest building can conceal an elaborate machinery beneath it. A quiet person can contain histories no casual glance would ever infer. We are repeatedly fooled by surfaces that appear proportional to their interiors. A small red dwarf with a giant planet belongs to that same family of correction. The visible scale of the host does not neatly reveal the possible scale of the outcome. And once that lesson lands, it starts to rearrange more than one thing. You look at the category differently. You look at the word should differently. You even look at discovery differently. Because the deepest scientific discoveries are often not the ones that announce a wholly new phenomenon, but the ones that expose where an old phenomenon had been mentally fenced too narrowly. Giant planets were already known. Red dwarfs were already known. Planet formation around disks was already known. Nothing in the ingredients is new. What is new is their combination, in a setting that our smoother understanding had learned not to anticipate comfortably. Sometimes novelty lies not in a new object class, but in a new permission structure inside reality. That kind of novelty tends to age well, because it does not depend on shock value. It depends on revised relationship. After this, a red dwarf is not quite the same conceptual object it was before, at least not if we are being honest. It now belongs to a category that has produced something our habits of expectation had not fully allowed. The category has thickened. It has become more expensive to simplify. More expensive, too, to let a single narrative dominate. Core accretion remains the leading framework for much of planet formation, and for good reason. Disk migration remains real. Variations in disk properties remain important. None of that goes away. But a discovery like this quietly forbids intellectual laziness. No one clean sentence about low-mass stars and giant planets is allowed to sound fully settled now. Even the right sentence must carry more caution than before. It must leave room for the observed system, for the possibility of additional systems, for the fact that galaxies make statistical use of pathways that individuals might dismiss as narrow. There is something almost moral in that widening of room. Again, not moralistic, just morally clarifying in the older sense of forcing us to distinguish between what we know strongly, what we know weakly, and what we merely repeated until it sounded strong. The universe is relentlessly good at drawing those lines if we let it. And we let it through observation, through patient, repeated, often unspectacular observation. That may be the most beautiful hidden architecture in the whole story. We do not learn these things by dramatic confrontation with the cosmos. We learn them by staying with weak signals long enough for them to become meaningful. That requires a kind of cultural patience that modern life does not always reward. It requires institutions, instruments, persistence, follow-up, skepticism, and the willingness to let a tiny dip in brightness become the start of a larger revision. That is what happened here. A faint star dimmed in a repeating pattern. The pattern held. The object emerged. The implication widened. The category shifted. A word like should lost some of its authority. The galaxy became a little less over-compressed. And once the compression lifts, something else becomes possible. Gratitude, perhaps, but not the soft kind. A more exact gratitude. Gratitude that reality is not arranged only to satisfy our first-order intuitions. Gratitude that the ordinary remains capable of correction. Gratitude that the commonest stars, the ones most likely to be filed away as background, can still force a serious rethinking of what planetary systems may be doing across the Milky Way. That gratitude is tied to witness. We happen to live at a moment when a species on one planet can infer the existence of another planet from a fraction of missing starlight, and understand that this missing light is not just a detection, but a challenge to its own simplifying instincts. That is an extraordinary condition to find ourselves in, not because it makes us central. If anything, it does the opposite. It lets us watch ourselves being decentered by better evidence. A tiny red dwarf, somewhere out in the dark, has become one more teacher of that lesson. It has not done so loudly. It has not asked for myth. It has simply gone on existing with a giant planet in orbit around it. And in doing so, it has made one of the universe's most familiar categories feel slightly less finished, slightly less obedient to shorthand, slightly more alive than before. That aliveness matters, because it changes what the night means, not only as scenery, as inventory, as possibility. We are no longer looking at a sky made of neatly behaved classes. We are looking at a sky in which the quiet majority may still be carrying architectures that complicate every easy statement about what small stars can and cannot do. And once you feel that in full, something very subtle happens. The discovery stops sounding like an exception report and starts sounding like a correction to our sense of the ordinary itself. Because in the end, that is what this planet really changes. Not the laws of physics, not the reality of planet formation, not the fact that small stars, on average, still offer leaner beginnings than larger ones. What changes is our confidence in how complete that average was allowed to feel. A giant world around a tiny red dwarf does not overthrow the framework. It reveals where the framework had become emotionally overbuilt. It shows us the seam between a useful description and a too comfortable one. That is a smaller claim than the loud version, and a far more powerful one. The loud version says science was wrong. The deeper version says science was working, and in working, had begun to produce a story smooth enough that many people forgot how provisional some of its boundaries still were. Then, a dim star and a large planet reopened the boundary, not by argument alone, by being there. That presence is the final thing worth honoring. However many explanations we test from here, however the population statistics evolve, however many similar systems eventually join this one, TOI-6894b has already done something permanent. It has entered the category. It has changed the burden of speech. No future sentence about what giant planets do or do not do around very low-mass stars gets to float free of this world. The planet is now part of the atmosphere of the subject. And atmosphere is often where understanding really lives, not in isolated facts, but in the changed pressure around a whole field. After a while, people stop saying the old sentence in the old way. The caution deepens. The map gets rougher where it used to look smooth. Younger researchers enter the field after the correction and inherit a better instinct than the one that came before. The discovery becomes part of the discipline's nervous system. That is how knowledge matures, quietly and then all at once in retrospect. For the rest of us, the effect is simpler but not smaller. A red dwarf no longer feels quite as easy to summarize. The commonest stars in the galaxy no longer feel like they belong to a fully domesticated category. The night sky becomes less sordid in the mind. Not chaotic, not mystical, less sordid, more exact, more alive with the possibility that the background contains histories and structures our first simplifications were never going to catch. There is a kind of mercy in that. The universe keeps refusing to become merely decorative. It keeps denying us the cheap comfort of thinking that once a pattern is broadly understood, the category itself is finished speaking. Again and again, reality returns to its quiet populations, its background systems, its ordinary settings, and reveals another layer of hidden variance waiting there. A faint red dwarf with a giant planet is one more expression of that refusal. And once you have really felt it, the title changes meaning in your hands. A planet that shouldn't exist around that star begins as a line about impossibility. By the end, it becomes a line about misplaced certainty. The planet was never the one making the mistake. The mistake was in the degree of finality we had started to assign to our expectations. The mistake was in how effortlessly should had drifted toward can't. The mistake was in forgetting that a trend, even a strong one, is not a prohibition. That may sound like a technical distinction. It isn't. It is one of the deepest habits of thought science can teach. Reality is full of regions where what usually happens is not the same thing as what reality permits. Those regions matter enormously. They are where hidden pathways live. They are where tails of distributions become populations. They are where a galaxy's true variety exceeds the confidence of its neatest summaries. And often, they are where the most common categories stop being generic and start becoming strange again. That is what has happened here. Somewhere in the dark, a star too small to match our instinctive image of a star is carrying a giant world around itself every few days. The system is real. The mismatch is real. The theoretical discomfort is real. The larger implication is real too. If even the galaxy's quiet majority can produce arrangements like this, then the Milky Way is still less intuitively understood than many of our cleanest sentences suggest. There is no need to exaggerate that. It is enough. Enough to make the common stars feel less common in the mind. Enough to make the word ordinary lose some of its laziness. Enough to make a tiny dip in starlight feel like a widening crack in a comfortable story. Enough to remind us that the universe does not have to shatter our models to humble them. It only has to keep being itself at the edges of our confidence. And maybe that is why discoveries like this linger so well at night. They do not leave you with a slogan. They leave you with a changed background. You can look up at the sky later, or simply think about it in the dark, and the stars are no longer just stars in the old simplified sense. Hidden among the ordinary points are systems whose very existence would once have sounded like a bad fit. Quiet hosts carrying extravagant companions. Modest-looking settings hiding more permissive histories than our instincts had granted them. The calm majority of the galaxy, still not done surprising us. That is a beautiful correction, because it does not make the world less lawful. It makes it less complacent, less over-translated into human comfort, more faithful to the actual richness of process, timing, probability, and scale. We are left not with disorder, but with a truer kind of order, one in which the commonest things are not automatically the simplest, and the background is not automatically understood just because it is everywhere. So a faint red dwarf, a giant planet crossing its face, a brief loss of light, and from that slight dimming, a whole chain of human confidence adjusting itself. Not collapsing, adjusting. That is how the universe often changes in our hands, not by becoming unreal, but by becoming more real than our shorthand was. Not by shouting, but by persisting. Not by giving us less to trust, but by teaching us to trust with finer edges. And there is something profoundly moving in the fact that consciousness can witness that process at all. On one world, around one star, beings made of temporary matter have learned to watch the light from another small star, notice a tiny recurring absence, and understand that the absence means a planet is there. A planet large enough, and strangely placed enough, to loosen one more knot in how we thought the galaxy was arranged. It means the ordinary sky is still not ordinary. It means the commonest stars may still be keeping some of their largest secrets in plain sight. It means the world does not get simpler the closer we look. It gets more honest. And somewhere beyond our sight, that little red star goes on holding its giant companion in the dark, while our categories, slowly and properly, learn how to make room for it.